Good morning, dear students. My name is Manush Kumar Gupta. I am the assistant professor in the Department of Mechanical Engineering, Haldia Institute of Technology. Today we will start with a new concept of the continuation of the previous chapter, that is the CFD lecture number 2, continuity and momentum equation. In the previous classes, we have learned about the CFD. So we have come to know what is CFD. It is the mathematical modeling of continuum problem lead to the set of differential equation. Also, we have learned the historical perspective of CFD, what is the uh, earlier approach, how it was developed. So all we have learned in the previous chapters. Also the al- algorithm front, earlier applications, such kind of things we have learned in the historical perspective. Also we have learned the application of CFD. There are different fields where we can find the use of CFD, such as meteorological, aerospace design, turbine machineries, such kind of things. All these things or all these stuff we have learned in the previous classes. Followed by there are some advanced knowledge will be acquired in the uh, forthcoming classes. Now today we will start uh, about the continuity and momentum equations. As you know, these two equations are based on the general uh, concept of physical science, that is physics. Uh, we will, I will start today the lecture by discussing the principle of mass conservations, also known as the continuity equations, and the principle of momentum equations. As you know, the principle of mass conservation is that mass neither be created nor be destroyed. It is in the form we consider a fixed control volume in space. The equation tells us about the rate of increase of mass inside the volume plus net flux across the control surface. So that concept will be used here for the derivations of continuity equations. So first we'll go for the continuity equations. So in continuity equations, we know that mass is conserved. Next we'll learn about the uh, momentum equations, which comes from the principle of Newton's second law, where the force is F, which is equal to m into a. So F is m multiplied with a, where m is the mass and a is the acceleration. So these are the basic physics, all you have learned in your previous classes, in the 12th or maybe in the 11th standard. So the purpose of this topic today, what we are just going to learn, is to derive and discuss the equations. Okay, because we all know CFD is based on these equations. It is important for all of you to feel very comfortable with these equations before continuing further with these studies. The fundamental physical law, as you know, already we have discussed here. The mass is conserved. Second, the Newton's second law, and third one is the energy is conserved, which is known as the energy conservation law. When these three laws we will apply for the CFD study, we will develop a model of the flow, any flow. And this model, also in the previous class we have discussed, there are three approach, which is already we have discussed the finite difference method or approach, finite volume approach, and the finite element approach. Okay, so these three equations, first one is mass conservation. Second one is the momentum, momentum, and third one is the energy. So that would be applied for the model of flow structure. Okay, so these three laws will be applied for the study of CFD, which are known as the governing equations of fluid flow. Okay, so this mass conservation law give you the continuity equations. So this give you the continuity equations, and momentum, that is the Newton's second law, would give you the momentum equations, which comes from the concept of Newton's second law, and the energy equations where the energy is conserved. So these three equations is known as the governing equations, which will be used for solving the uh, main fundamental or governing equations. The model of the flow again will be employed, okay, for fixed finite control volume. Second one, moving finite control volume, and third one, again, the fixed infinitesimal small volume, and fourth one is the moving infinitesimal small volume of fluid element. So, I want to say you that there are actually two approaches. One is finite control volume approaches, and another is the finite uh, infinitesimally small volume approach. And one is fixed, and another is moving. Okay, so these will be called the model of the flow. Finally, these three governing equations will be applied to form a form which is particularly suitable for shaped study with the proper application of some boundary conditions such as inviscid flow and for viscous flow. Okay, now going back to the third slide, we will be studying here uh, the visualized derivations of these equations. Okay, of these equations. Here in this slide, we are applying the Gauss divergence theorem, which was already discussed in the previous class, which is used for, as you know, to convert surface integral into the volumetric integral. Okay, so applying this Gauss divergence theorem is very much important for the study of CFD. Okay, now we will go for the finite control volume approach. Okay, so already we have discussed there are two approaches. One is the finite control volume approach, finite control volume CV, and second one is this is the first one approach, and the second one is the infinitesimal small, in very small, okay, infinitesimally small fluid element. Okay, and for the first one there are two cases. One is when the fluid flow is in fixed, and again the second approach is when the moving control volume is moving with the fluid. Okay, so these two approaches again will be applied for the infinitesimal small element. For both the cases, there are actually two cases. One is fixed cases and another is moving cases. Okay, suppose, so this is a control volume, so CV. Okay, here these are the streamlines. Okay, so obviously it has some volume, so which is fixed. Okay, which is fixed in the space with the moving flow over it. Okay, and second case is again that control volume, which having the volume is V, which is surrounded by the surface S here. Okay, so this finite control volume moving with the fluid, so it moves with the fluid. Okay, so it moves with the fluid. So these are the streamlines, such that same fluid particles are always within this same control volume. So whatever fluid will be inside within this control volume, since it is moving with the fluid, so that would be remain unchanged. Okay, but for earlier cases, it is fixed. It is fixed. So the this control volume, um, which is fixed in here, the fluid flow would be moving through it. Okay, so these two concepts, this is the two concept for finite control volume approach. Okay, next approach is the next approach is the what? Next approach is the infinitesimal small infinitesimal small fluid element. Okay, small fluid element. Suppose you see here, this is a small fluid element. Okay, this is 3D cases. Okay, So here this is the streamlines. So this arrow shows the direction of the streamlines. Here this infinitesimal fluid element is fixed with that space, means it is not moved. Okay, it is not moved with the flow velocity. Okay, so this is first case, and second case it can also be moved with the flow velocity, uh, v. Okay, so same fluid element. Okay, same fluid element is moved with the flow velocity. So this is the tangent where this v is the velocity vector. The velocity of that element is equal to the flow velocity. Okay, so here also you will again apply the two approaches. Okay, so when any finite control volume or the fluid element, very small fluid element, okay, is fixed with the space coordinate, so that approach is known as the conservative approach. Okay, which is known as the conservative form of governing equations. And the next form, which is moved with the flow velocity, is known as the conservative form of governing equations. So always keep in mind, there are two terms here, actually conservative, which is fixed, conservative form, FORM. Second one is the non-conservative form, non-conservative form. Okay, so which is move along the flow velocity. Okay, so going to the next slide, we will derive the differential control volume. Okay, so first approach for a finite control volume method, which is fixed in the space. Okay, which is fixed in the space. Again, we will also have to know the divergence of the velocity. Okay, and six physical meaning. Okay, so what is divergence uh, of the velocity? We will have to learn here. Okay, so this is not a simple task, but the concept would be very simple. Okay, the concept would be very simple. Suppose, so this is, I am drawing a figure here. This is a control volume, okay, which is bounded by a control surface S denoted as surface S. Okay, so this is the control surface. Here within this control volume, I have taken an elemental sections, okay, whose area is ds. Okay, so since it is a 3D, so obviously that dimensions I am elongating here. Okay, suppose within this elemental volume there is a n, the normal vector, and this arrow shows the direction of the velocity. Okay, now this is ds. Okay, this is ds. Now we'll form the equations based on this figure. Okay, here n is the normal unit vector. Okay, normal unit vector, which is acting perpendicular to the surface at ds. Okay, now we will determine the volume, VOLU, volume of the elements. Okay, volume of the elements, or control volume. Okay, control volume, which is denoted as del V here. Okay, del V. So that del V will be determined, okay, as the velocity. This is the velocity which is multiplied with the time. So suppose for a fraction of time, that is the del t. Okay, this multiplications along with the normal vector. Okay, along with the normal vector is nothing but the displacement. Okay, so if that displacement, okay, is multiplied with the elementary surface area, that is gs, so we will get the volume of that elemental strip. Okay, here. So again, it is written as v del t multiplied with the capital ds. Okay, where this capital ds is nothing but a n into normal vector into small ds. Okay, So this is we are denoting here. Okay. Now, if this ds is the surface area, total surface area, is denoted as capital DS. Okay. Over the time increment del t, we will now have what? We will now have uh, get the or calculate the total change of volume of the entire control volume. Okay, of the entire control, and it would be possible to get this by the method of surface integral. Okay, so the total volume now would be the total volume. So it would be that's nothing but the surface integral of v into del t, that is the time over elementary time, into ds. Okay, now again we'll have to find out the time rate of change of volume. Okay, since the flow is moving, since the element is moving, so here the approach would be the substantial approach. Okay, substantial approach. So that is known as the total derivative. That is known as the total derivative. Okay, so that would be denoted as that would be denoted as that would be denoted as the caps dv dt over that time del t. Okay, that surface integral is okay. So v into dt into ds, okay, into ds. So again it is equal to surface integral s v into ds. Okay, so this is the things. This is the things. Next, we will apply the Gauss divergence theorem. Okay, that is the surface integral now will be converted to the volume integral. So how we will convert this? By applying the Gauss divergence theorem. Okay, so since it is moving, so caps dv, okay, by dt, that would be equal to the surface, that is the volume integral d. Okay, one Nabla operator will be coming here into the pictures. Okay, into dv. Okay, so that surface integral in the previous cases, what we have written here, that surface integral is now converted to the volumetric integral by the application of the Gauss divergence theorem. Okay, since if we imagine that the moving control volume is stuck to a very small volume. Okay, so it is very small volume if we consider. Okay, essentially it's become the infinitesimal moving element. Okay, infinitesimal if we shrink that volume into a very small volume, then what will happen? So this term, this integral term now have become zero. Okay, now have become zero. So for that case we can rewrite that equations. Okay, so dt, okay, so now it is written as dv because we are shrinking that volume. So we can omit that one. So Nabla operator v into dv. Okay, Nabla operator dv. Now from this, what we can get for the next steps, we'll be getting that the Nabla, that is the divergence. Nabla dot product. Okay, divergence is nothing but 1 by del v into ft del v divided by dt. Okay, so these equations will give the significance of the divergence. Okay, so that term physically signifies that the time rate of change of volume of moving fluid element per unit volume. Okay, so this is the divergence concept we'll have to learn. Okay, now here you see how you will get that equations. Okay, so this is the continuity equations. How we will get this, we will derive from that concept. Next, going to the next slide, we will now derive the momentum equations. So before going to the momentum equations, we'll have to learn about the we'll have to learn about the continuity equations. Okay. So continuity equations, this is the exact form of the continuity equations. This is the exact form of the continuity equations. Okay, this one, this equations is the form of the continuity equations. Now we'll go for the derivation of the momentum equations. Momentum equations. So this slide shows you the integral form of the momentum equations. The left hand side of that equations includes the time rate of change of momentum, okay, which is denoted as del P within the volume, and the net momentum flux across the surface. Okay, so the right hand side of that equations we see here the contributions from surface forces. Okay, first one is the viscous force and second is the body force. So S here is the surface force and B is the body force. Okay, so force here, surface force actually comes under the, there are two types of surface force, pressure force, you already know, and the viscous stress. Okay, and body force, you know, the gravity for the analysis in fluid mechanics problem, gravity is the main body force which will be applying or which will be applied at the center of gravity of any object or any body or any fluid container. Okay, so the expressions of surface force is the integral form of the shear stress over the entire area. Okay, and the body force is nothing but the rho into B into dV, where B is the body force per unit mass. Okay, over the integral of the whole volume. Okay, so this is the integral form of the whole volume. Okay, so this is the momentum equations of the integral form, momentum equation of the differential form. Okay, to obtain this local version of the momentum equations, we again apply the divergence theorem. Okay, here, and being all terms to a appropriate pointwise formulation. Okay, we arrive at these equations where the divergence of the momentum flux equals the sum of the body and the surface forces. Okay, we can also write the equations using the material derivative, which is also known as the substantial derivative, which gives the non-conservative or Cauchy form of the momentum equations. This form is particularly helpful when focusing on particle-based or Lagrangian formulations. Okay, so this is the equations you should have to know about or keep in mind. Now going to the next slide, that is the momentum equations in the differential form. Okay, so here we see the momentum equations broken down into the x, y, and z components. Okay, x, y, and z components. The left hand side represents the inertial term, both local accelerations and convective accelerations in each directions. So this is the local derivative parts, and this term is the convective. Okay, and this is the diffusion parts. Okay, and this is the body force. Okay, now the alternate form of that uh, equations using the material derivative form. Okay, since it is in the moving concept, so the substantial derivative or total derivative f dv dt multiplied with the rho that will come in the left hand side of the equations. This term, okay, this whole terms will be written as rho times caps dv dt. Okay, and the right hand side as it is. Okay, so this is the conservative or Cauchy form of momentum equations. Understand? Next, the momentum equation component form in the Cartesian coordinate systems. Okay, here let's interpret the term physically. Okay, on the left hand side we have the fluid accelerations. Okay, so this is the fluid accelerations. So this term, this is the local derivative, and this is the converting term for x component equations. Okay, so how fast it is gaining or losing momentum at that point. So this is the significance. On the right hand side of that equations, we have focuses the derive these changes. Okay, derive the changes. Pressure gradient, push or pull the fluid. Pressure gradient. Pressure gradient here, pressure terms actually will be the surface force. Okay, will be the surface force. that would be written over here, special force. Okay. So it would be, since it is along the x component, so del p del x, and one term will be coming here and y root. Okay, understand? Similarly, for y component, so that you would be uh, replaced by small v, and for z component, that you for x component, that will be replaced with the small w, because v is the velocity vector, which is nothing but I u plus j cap, okay, or polar cap, small v plus k cap of w. Okay, so it's u v w are the component along the x, y, and z directions. Okay, so this is the momentum equations in the final form for all the three coordinate system. Okay, next we'll go for slide number 9. Okay, slide number 9. So comparison of the form. Okay, comparison of the form. So this slide compresses the different form of governing equations. Okay, integral form describe the integral forms describe the global balances over finite volume and are best suited for finite volume method. Okay, method. Differential form of describe what is happening at the each point in the flow. Okay, conservative forms, as you know already. Okay, form that preserve the fluxes exactly. Okay, a key features for shock capturing schemes. Okay, so that will be the main physical interpretations. And for non-conservative form, it is useful for analytic derivations in the MSD method. Okay, knowing which form to use essentials when setting up the CFD simulations. Okay, so the left hand side and the right hand side term we will have to know properly. Okay, uh, obviously the left hand side part already you discussed here. This is the local derivative, and along with the convective terms. In the right hand side, the pressure gradient force already we have put it in here. We have added there this term. Okay, and the viscous terms, the CR and normal stresses. Here you will see the this is the normal XX, YY, and ZZ. These are all normal terms, and these are okay. These are the shear terms. Okay, shear terms. The shear stresses. Okay, and only the body force is the gravity. Okay, so this is the foundation of the NS equation. That is the Navier-Stokes equation. Now we will compare each of the form of equations. Okay, each of the form of equations. So integral form, here we will, the main feature is like the global balance over the control form, integral form. Okay, differential form, pointwise and local expression of conservations. Conservative form already you are known when this is fixed. Okay, with the twist at the phase coordinate, where the free particle are going over the control volume. And non-conservative form emphasizes the accelerations and turbulence, where the control volume as well as the incrementally small free particle will be moving along with the flow velocity or fluid. Okay. Next, this is the summary. Okay. Here I have derived the continuity momentum equation in both integral and differential form. These equations are the foundations of CFD and describes how fluid mass and momentum evolve in times and space. That is called the spatial temporal approach. Okay. In our the next lectures, we will explore the energy conservation equations and begin discussing the boundary conditions. Okay. So today after this, in the next class, we will learn the new concept of energy equations. Okay. Thank you. Thank you, dear students.